So today what we will do is to look at this in a more general context and write down multidimensional Fokker-Planck equations and apply it to the case of particles moving in phase space itself. So to recall to you what the equations were, we had an equation which said x dot minus v was equal to 0, that just says the velocity is the derivative of the position, and then v dot plus gamma v, this is the friction part, the systematic part of the random force on it. This was equal to square root of gamma over m eta of t, where this was Gaussian white noise. In other words, it is a delta correlated Gaussian process, stationary Markov process, which is delta correlated with unit strength. So eta of t equal to 0 and eta of t prime equal to delta function of t minus t prime. Okay. And now the question is, what is the corresponding Fokker-Planck equation satisfied by the probability, conditional probability density in both x and v jointly. So we are asking for the equation satisfied by p of x v t, given that it started from x naught and v naught at time 0. It is important to remember that earlier we had equations only in v, and of course the equation satisfied by v was the Fokker-Planck by v was the Langevin equation. We got a Fokker-Planck equation for it, and the solution turned out to be the Ornstein-Uhlenbeck distribution, and we discovered also that the velocity process was exponentially correlated and that it was a stationary random process. Okay. So that much we have already seen. Now the question is, what does this look like? What equation is satisfied by this quantity here corresponding to this set of equations here. Now it turns out that if you have a general process, a multidimensional process of this kind, if you put them together in some vector form and you call that a vector xi, say xi dot, plus if you got a linear drift r xi, this is some constant matrix here acting on this column vector here. If this is equal to, on the right hand side you have the usual noise of some kind, so we have gamma over m and then eta as a vector or eta of t, and this stands, this quantity xi stands for x and v, and this eta of t stands for 0 eta of t. There is no noise here in this equation, but there is a noise, driving noise on this side due to the collisions with the other particles in the fluid. If you have a Langevin equation, a stochastic differential equation of this kind, corresponding to it, this quantity xi, its conditional probability density satisfies a certain Fokker-Planck equation, and that Fokker-Planck equation is given by the following. It is given by delta over delta t, and let me call it rho. Let me call this rho so that you know that it is a phase space density. This is equal to, on the right hand side you have Rij delta over delta xi j rho, that is the drift term, the first term, plus a Dij d2 rho over delta xi delta xij, where this matrix Dij is in this case a 2 by 2 matrix which is 0 0 0, and then whatever was the matrix which came out from 1/2 the square of this guy here. But remember that consistency required that gamma was equal to 2m gamma k Boltzmann t. That was the fluctuation dissipation theorem. This is what kept the velocity in equilibrium. The Maxwellian was retained in time. Then 1/2 the square of this guy the 2 goes away, there is an m on top comes, and that m cancels out here with this m squared and give you a factor m in the denominator. So you are going to get gamma k Boltzmann T over m. That's what this guy is, and that's the Fokker-Planck equation. Okay. All we have to do, and there is a summation over repeated indices, I and j run over 1 and 2. Okay. Now in this problem, what's r? Well, from these two equations it follows that r in our problem here is equal to 0, -1, 0 and gamma. So r12 is -1, r21 is 0, there is no x here, and then r22 is gamma out here, and that is it. So that is the Fokker-Planck equation. All we have to do is to write it out explicitly, and you immediately see that delta rho, this thing here, is equal to, in this particular problem, r12 is a minus sign, so there is a minus delta over delta I is equal to 1. So there is an delta over delta xi I, r12 is what we need. So this is equal to 1, that gives me a minus delta over delta x, and this is 2, so that is a v times rho out here, and that is it. There is one more term which is r22, which is delta over delta v gamma v rho, that is the 2 part, plus the only term that survives in this term here is d22, that is the only non-zero element here, and then it becomes delta v2. So plus gamma k Boltzmann T over m d2 rho over delta v2. That is it. Okay. Now of course v is independent of x because it is a dynamical variable, it is independent of x. So this is equal to minus v delta over delta x rho plus gamma times delta over delta v rho plus gamma k Boltzmann T over m. This is the Fokker-Planck equation satisfied by rho. It is a fairly complicated partial differential equation. This portion was already there in the Fokker-Planck equation satisfied by the conditional density of the velocity itself. So was this, but there is an extra term here out here, and this is like a convective derivative because it is v delta over, it is like v dot del in 3 dimensions, it is a 1 dimensional analog of that. So if you bring it to the left hand side, you have d by dt, d over dt of rho, the full derivative, equal to whatever is on the right hand side with this linear drift and this extra diffusive term here. Now the question is, what is the solution? Well, it depends on the initial condition, and we are talking about this conditional density. So at t equal to 0, this satisfies rho of x v 0 at x naught v naught is delta of x minus x naught delta of v minus v naught. So with that initial condition, if you solve that partial differential equation with the boundary condition that these things vanish as x and v tend to infinity, you get Gaussians as the solution finally. We are not going to do that here, but you end up with some complicated Gaussian solution, okay, a bivariate Gaussian both in x and v. So it will have terms like e to the minus x squared minus e to the minus v squared and e to the minus plus xv, there will be cross terms. Okay. The interesting question to ask is, what happens to this as t tends to infinity? In this problem, t tending to infinity means t much greater than the velocity correlation time, gamma inverse. So it turns out that rho of x v t given x naught v naught tends, as t becomes much bigger than the correlation time, it tends to the Maxwellian in v, and the Maxwellian in v is of course m over 2 pi k Boltzmann T to the power half e to the minus v squared over 2 k Boltzmann T. So the velocity thermalizes, and then you have the positional part, and that of course is 1 over 4 pi dt to the power half e to the minus x naught whole squared over 4 dt. you will recognize this to be the limit of the Ornstein-Uhlenbeck distribution as t tends to infinity. That is just the equilibrium Maxwellian distribution, and that is the solution to the ordinary diffusion equation. The question is, what is this capital D, and we saw by comparison of the Langevin equation with the diffusion equation in the long time limit, we also saw that the other consistency condition was D is kT over m gamma. Okay. So is there an equilibrium distribution? No, because as t tends to infinity, this vanishes out here. So it says that there is no stationary distribution for ordinary diffusion at all, everything goes to 0, the whole Gaussian goes down, flattens out to 0. The velocity, however, thermalizes. The velocity is a stationary random process, it thermalizes. Okay. One could ask, alright, this is the phase space density, what happens if I integrate over one of the variables? I should get the distribution in the other variable, right? So if you did this, if you took the exact solution, if you did integral over dx rho of x vt x naught v naught over the full space, what should this give you? What would you expect it to give? It should give you, well, it should be still a function of time, because all you have done is to take the joint distribution in x and v and you have integrated over the position. So it should give you the conditional density in the velocity alone. And what is that distribution? It is not the Maxwellian, that is the limit distribution, the Ornstein-Uhlenbeck distribution. So it will end up with exactly the Ornstein-Uhlenbeck distribution. So this thing here will become m over 2 pi k Boltzmann t 1 e to the minus 2 gamma t, that is the variance to the power half exponential of minus v minus the mean value, which is e to the minus gamma t. Remember, this is conditional on this initial condition always. So it is this squared, divide m times that over 2 k Boltzmann t 1 minus e to the 2 gamma t. This is the Ornstein-Uhlenbeck distribution. So indeed, it will turn out after you integrate over the position, you end up with this. Okay. What would you expect if you integrate over the velocity instead? What do you think you will get if you did minus infinity to infinity dv rho of x vt x naught v naught? What should you get? What would you expect? Would it be this? Would it be this? What does your intuition tell you? Would it be that distribution? I got rid of the velocity altogether. So do you think it would be that distribution? Yes. That is only valid in the diffusion limit. That is only valid for t much greater than gamma inverse. We are not saying anything like that here. We are just integrating over v. So what would you expect? It is the positional distribution, no doubt about it. It is the positional conditional distribution density in the position. It will be a Gaussian, because you have got a bivariate Gaussian, you are integrating over one variable, you are going to get a Gaussian in the other variable, no doubt, but much more complicated than that simple diffusion equation solution. It is some Gaussian. You need to know the exact solution of this equation in order to be able to do that. I am not going to write it down here, I will give it to you in writing elsewhere. It is a complicated formula, but that distribution will tend, as gamma t tends to infinity, will tend to that diffusion equation solution. Okay. And interestingly enough, there is no simple formula here. Whatever distribution you get here, that does not obey any simple master equation. Okay. So although the phase space density itself obeys this master equation, the Fokker-Planck equation, and the velocity process itself obeys a Fokker-Planck equation, the position does not obey such an equation, simple equation at all, except in the diffusion limit when you go to this long distance. And in fact several ways of seeing this, that the position is not stationary random process. We will talk about the Wiener process very shortly, and then you will see how complicated the position actually can become. Okay, and what Brownian motion means and so on and so forth. Okay, so much for this, that this distribution has an asymptotic limit which does this, and when you integrate over the position you end up with the Ornstein-Uhlenbeck distribution. Now we can generalize this a little bit, go a little further. We can ask what happens if I had an external force on the problem. What would then be the effect of an external force? Well, one way to approach this is to look at a slightly different model. Instead of a free particle, let us look at the problem of an oscillator, a simple harmonic oscillator. Now what we are talking about is a particle on the x-axis, here is x equal to 0, and this is a simple harmonic oscillator in the absence of any external force. But we now imagine it is in a fluid with viscosity, and this particle is being hit randomly by the other particles in the fluid, okay, and we want a Langevin type model for its motion here. So there is a white noise exactly as in this case, but there is also a systematic part of the force which corresponds to putting in the harmonically bound particle, namely this thing is in a potential. Now this potential is going to do something interesting. The actual harmonic oscillator potential is half m omega naught squared x squared, as you know. Now the first effect of this potential is that the translation symmetry on this x axis is lost, because this point becomes a special point. There is a potential here. The other thing is it is as if this particle is connected by a spring, a harmonic spring, to the origin, and therefore there is a strong restoring force if the displacement is very far away from the origin. So you might expect, okay, there is going to be two effects here. One of them is the random force due to the other particles, which is tending to diffuse, move this particle away and make its mean square displacement diverge as a function of time. The other effect is this restoring force, which is always acting. Now the question is, what is going to happen to this particle? Will it diffuse or will it not? Will the variance of the displacement diverge as t tends to infinity? If it does so linearly, you know that it is diffusive. If it goes to a finite constant, then you know it is not no long range diffusion at all. So the question is, what is going to happen? So that is the physical question. We can answer it in the following way. I can write this down by adding to this the restoring force, and that of course is minus m omega squared x, and I have divided out by m. So there is also a term v dot plus gamma v plus omega naught squared x. Let me call it omega naught, the unperturbed frequency of this oscillator. So this is the case of a harmonically bound and that is the equation. Everything else is unchanged, exactly as it is. Now of course the velocity once again thermalizes, and there is an equilibrium velocity distribution, which is again the Maxwellian distribution as before. But there is also this potential energy term coming from the potential in which the particle is. Okay. So now what happens? Exactly as before, I can write down the same problem. I have rho of x Vt, and we could start it from 0, for example, just to make sure that it is a simplest condition, but whatever it is, given some x naught, given some v naught at 0, the question is, what does this particle do? What does the density satisfy? Again, the same Fokker-Planck equation as before, same as this exactly, but whereas in the previous case this fellow was equal to 0, r was equal to 0, minus 1, 0, gamma. What is it now? Remember, there is an extra term here, omega naught squared, and this is appearing with a coefficient x in the equation for v. Okay. So it means there is a term here which is omega naught squared. That is the only difference between the two. everything else goes through exactly as before. So there is going to be here another term which is equal to plus, there is a term which is equal to delta over delta, and what would this be? It is in the V equation. Okay. So R21 is what contributes, so this is delta over delta V omega naught squared x rho, this is a term of that kind. Okay. Because it is going to contribute to a delta over delta V because it is R2 and this is a 1, so there is an x inside, omega naught squared x. Okay. That is the only change, and we have an exact answer for the Fokker-Planck equation satisfied by a harmonically bound particle in phase space. And of course omega naught squared is constant, so let us write that out. So let us write this as equal to minus V delta rho over delta x plus omega naught squared times x times delta over delta V, delta rho over delta V. Because this time x is independent of V, so that comes out. Just as out here V was independent of x, so it came out. And that is the Fokker-Planck equation. Now the solution to this is very different from the solution in the absence of omega naught altogether. Okay. What do you think will happen? Physically, what do you think will happen? Think back to equilibrium statistical mechanics. If you have a free particle, free gas, the position is irrelevant and the position is equally spaced, distributed entirely in the container, then it is only the velocity that is relevant. Okay. So gas in thermal equilibrium, classical gas, you only talk about its velocity distribution at a given temperature. The position is taken to be uniform throughout, but now there is a harmonically bound particle. So it is clear that the energy of this particle, there is a contribution which is half m omega squared x squared to the potential energy of this particle, and we know that the relative probability of any value of the energy is e to the minus epsilon over kT, right. So you would expect to get in equilibrium the distribution would be biased towards x equal to 0, obviously most probable value of x would be 0 in this case. And what is the actual distribution? It is the Boltzmann distribution, right. So what is the actual equilibrium distribution? Rho equilibrium of x and v, or the stationary distribution from equilibrium statistical mechanics, what would this be? It is e to the minus the energy over kT, and that is it, normalized, appropriately normalized. So this guy would obviously be e to the minus mv squared over 2k Boltzmann T, that is the kinetic energy part, minus m omega naught squared x squared over 2k Boltzmann T, that is the potential energy part, right, times normalization factors. E to the minus ax squared, where a is a positive constant, if you integrate you end up with square root of pi over a, so it's square root of a over pi is the normalization, right. So this thing here equal to square root of m over 2 pi k Boltzmann T square root of m omega naught squared over 2k Boltzmann T. This is the normalized distribution such that if you integrate over x and b, you are going to get unity completely. So the distribution factors into something in x, a Gaussian in x and a Gaussian in v, velocity. You expect this on physical grounds, this is going to happen, okay, and that is it. So this exact solution will reflect that, will reflect precisely this. Now tell me, does the variance of the mean displacement diverge as a function of time, do you think, or no? It cannot, because the limit value, limiting distribution in position is a Gaussian, and Gaussian has finite variance completely. So there is no long range diffusion. The behavior is not diffusive, it's tending to a Gaussian. It is going to do exactly what the velocity does except for a change of constant here and so on. Notice dimensionally everything is okay, because the Maxwellian distribution in velocity must have physical dimensions 1 over the velocity, so that P of v dv is equal to 1 when you integrate, right. So there is an m here and there is an m kt, which is ml square t to the minus 2, and the m cancels and you got an L square t to the minus 2 square root, which is LT inverse. So this whole thing, the velocity is in fact 1 over velocity, 1 over velocity in physical dimensions, and similarly this is going to be 1 over length, because the t to the minus 2 cancels here. Okay. So this is perfectly correct dimensionally, and you end up with distributions which are stationary distributions in this case. So the mean square displacement will not diverge. What will it be actually, the mean square displacement? What do you think this will be? What do you think v squared will be in equilibrium? What should this be? Kt over m, yeah, because half mv squared will have half kt, so this is kt, this is kbt over m, x squared in equilibrium. What will this be? Okay. No long range diffusion is possible. And that is reflected by the solution to this guy. Again, this is a bivariate Gaussian, this fellow here is a bivariate Gaussian, which will now tend, in as t tends to infinity, it will tend to this equilibrium distribution here. But there is an interesting wrinkle here. What do you think is the relaxation time for the position and the velocity? You can tell what this is by looking at these equations here, and in a minute you will see what the difference is in a minute. You see what happens is that the velocity thermalizes over a time scale gamma inverse. That is the correlation time of the velocity. But the position does not thermalize with that velocity, right. For instance, if it is an underdamped oscillator, it is clear that it is going to reach equilibrium values in an oscillatory fashion always. If it is overdamped, it is going to go monotonically and so on, right. So the omega naught and gamma together will provide 2 time scales in this problem. And what is the criterion for overdamping of an oscillator? Given this current natural frequency omega naught and a damping constant gamma, both of which have time dimensions of frequency. So you know that in this general expression you end up with gamma over 2, whether that is bigger than omega naught or smaller than omega naught, etc. This is overdamped. And of course less than omega naught is underdamped. We do not care what it is, this equation is valid in general. Whatever the value of omega naught and gamma be, this equation is true in general. And there is a complicated solution, a bivariate Gaussian solution. But the relaxation times of the two are different from each other altogether. We will see in a minute to show you what the relaxation, effective relaxation time is for the case of the position. Because you can also ask, in this problem in which I am telling you, I am asserting even without writing the general Gaussian solution down, that x does not diffuse, the behavior of the, there is no diffusion, long range diffusion here, and that there is a stationary distribution both in x and v in this case. Both x and v are stationary Gaussian processes in this case. So here if you integrate over the velocity, you will end up with the distribution for the position whose solution is some kind of Gaussian and describes a stationary random process. It is the distribution, conditional density is a stationary, that of a stationary Markov process. Similarly for the velocity as well. Okay. Now we could ask, can we quickly see what the position itself does? How do we get at it? Assuming that the velocity has thermalized, what would one do in this case? Well, this is what one would write down. I'd start with this second equation and write it in this form: x double dot plus gamma x dot plus omega naught squared x equal to square root of gamma over m eta of t. Okay. And then I look at the over damped oscillator case, in other words very high friction. So this is called the high friction limit. There is a systematic way of doing this. High friction. I have divided by m, but imagine putting the m here and saying this term dominates, very high friction, gamma is very large. Then the inertia term can be neglected. Okay. The effect of the mass is supposed to be light, the friction is supposed to be very high, and then m can be neglected, this original term. And then it becomes a Langevin equation, just like the velocity Langevin equation for a free particle, right? Except a slight difference here. So now you got an equation which says x dot plus omega naught squared over gamma x. Let us put it on the right hand side. So x dot equal to minus this guy plus square root of gamma over m gamma eta of t. That is the Langevin equation for the position in this limit. Okay. So let us simplify it a little bit, and what does this give you? This is equal to minus omega naught squared over gamma x plus, remember this was 2m gamma whatever it was, right, and there is an m gamma out here. So this is square root of 2k Boltzmann T over m gamma eta of t. In this limit, in this high friction limit. Okay. So that is the Langevin equation. Compare this with the Langevin equation for the velocity for a free particle. What did we get? We found that v dot, compare with v dot equal to minus gamma v plus square root of gamma over m, that was equal to square root of 2 gamma k Boltzmann T over m eta of t. Compare with that. So apart from this thing gamma here being replaced by omega naught squared over gamma, and then this constant changing to this other constant, it was exactly the same in structure, right. So what is the Fokker-Planck equation for this P here? So what is this going to be? P of xt, assuming that you start from some origin at t equal to 0, even x naught, we do not care, satisfies delta p over delta t equal to, okay. And what is the first term on the right hand side? This is a simple Langevin equation for which you can write the Fokker-Planck equation immediately, right. So this is equal to omega naught squared over gamma delta over delta x, because everything is in x, xp, that is the drift part, plus 1/2 the square of this guy, whatever this was, plus k Boltzmann T over m gamma d2p over dx2. That is the Fokker-Planck equation for p of x comma t, right. Do you recognize kt over m gamma? What is that? That is the diffusion constant. That is the diffusion constant. So what we have got here is what happens in the high friction limit to a harmonically bound particle as it diffuses. So there is a correction, if you like, due to the potential to the diffusion term. This is d, capital D. Without this omega naught, it would be delta p over delta t is d times d2p over dx2. That is the plain diffusion equation, and you have long range diffusion. But now you have got this extra term here. Okay. As soon as you have that, what does that imply? It says something very interesting. It says immediately that a stationary distribution would exist P of x as t tends to infinity, and it should satisfy an equation in which this term is 0, delta p over delta t is 0, right. It must satisfy stationary distribution P stationary of x must satisfy d over dx. So let us write it down, of k Boltzmann T over m gamma dp stationary over dx plus omega naught squared over gamma p stationary equal to 0. What I have done is to say this term is a function of x alone now, so this goes away, and I have just put that in, and this is it. Oh, there is an x, d over dx x times p stationary equal to 0, which implies of course that this comes out, and then if I take this down there, it says m omega naught squared over k Boltzmann T. Therefore, this is a constant independent of x. Okay, that is the current, and if you say the current is 0 at infinity, p stationary vanishes and so on, and derivatives vanish, then the constant is 0 everywhere, so we can get rid of this in an infinite medium, and this is equal to 0, implies p stationary equal to e to the power minus m omega naught squared x squared over 2k Boltzmann T. All I have to do is integrate x, and that is x squared over 2 with a minus sign, and then a normalization constant which is m omega naught squared over 2k Boltzmann T square root 2 pi, and that is the solution, which is exactly what you get from equilibrium statistical mechanics. So, we have got the Gaussian, stationary Gaussian there is no long range diffusion, etc. But the general equation is this here. This equation is the equation satisfied by a diffusing particle in the presence of an external force, a potential in this case, a harmonic potential in this case. It is called a Smoluchowski equation. This equation here is an example that term is generally applied to the diffusion equation in the presence of an arbitrary external force. We are going to apply it to other situations as well. For instance, if you put a magnetic field, if particle is charged and you put a magnetic field and it moves in 3 dimensions, and the question is what kind of probability density do the position and velocity and the phase space density have. That is a question we are going to answer, but this is the simplest example of a Smoluchowski equation. One can generalize this a little bit and say it does not have to be a harmonic potential, it could be any function, any force you like. We need that because we are soon going to do the case of a magnetic field. So, what do these equations look like? So, particle, let us write in a potential, let us say V of x. Let us write the phase space equation down and then see what happens. So again, let us do it in one dimension first, and then we will generalize this to higher dimensions. Okay. So you have x dot minus V equal to 0. But now, well, let us put the V on the right hand side, just x dot equal to V, and mV dot equal to minus m gamma V, that is the systematic part, and then there is a term which is minus V prime of x, that is the force on the particle, plus whatever is the random force, plus, so let us divide through by this guy as always, 1 over m plus square root of gamma over m eta of t. And now this V prime of x may be non-linear in x. That makes the equation extremely hard to solve because you no longer have a linear drift. Now we got a really hard problem on our hands. So the question is, what does this solution look like? What does this thing look like in general? What does the phase space density Fokker-Planck equation look like? Okay. So for this we need a slight generalization of the linear drift case where the drift matrix was given by R. Now it is some complicated nonlinear function in general. So let us say as usual that we have an equation of the form xi dot equal to some vector valued function f of xi. I have in mind putting this xi as the x's and v's depending on how many dimensions there are, all the dynamical variables, plus a multiplicative noise which is, let us say, g of xi on this eta of t. Okay. And let us be completely general. We do not know what the dimensionality of the xi is. If it is a particle moving in one dimension, then there is an x and a v. If it is moving in 3 dimensions, then there are 3 x's and 3 v's and so on and so forth. And we have so far been looking at the case where the noise is just in that single component of the velocity. But there could be different noises on different components. They could be completely uncorrelated noises. For instance, if the particle moves in 3 dimensions, you resolve it into 3 Cartesian coordinates, there is no reason to expect that all the forces in all the directions are identical. They are completely uncorrelated. In fact, what we will do and end up doing is to say that this force eta I of t, eta j of t prime expectation, where I and j are Cartesian components, would be uncorrelated with each other if I is not equal to j. So I am going to say this is equal to delta ij delta of t minus t prime. For instance, we are going to do things like that. So we need to keep that in mind. So let us be completely general and say that this is an n dimensional object. So I write it as a column vector, in other words n by 1 object, column vector of this kind. So is this. And this noise could be in some of the components, it may not have any noise at all in some of the others. For example, there is no noise here, no explicit noise. Okay. So let us say this fellow here is nu by 1. So it is nu dimensional white noise. There are nu of these guys, eta 1, eta 2 up to eta sub nu. Then this G in general, this would be an n times nu matrix, so that when it acts on the nu times 1, it is going to give you an n by 1. Okay. That is the general situation. Okay. Then corresponding to this equation, this implies, by this correspondence we have between a Markov process, the Langevin type equation for a Markov process and the corresponding Fokker-Planck equation for a diffusion process and the Fokker-Planck equation, we have delta rho over delta t equal to, in this case, delta over delta xi I times rho, okay, and summed over the components I, f I times rho plus delta 2 over delta xi I delta xi j dij, which could in general be a function of this xi, because this guy is times rho, where dij equal to 1/2, as you would expect, G transpose ij. Okay. This is a transpose. That is the generalization. Okay. Remember that G is an n by nu matrix. So, G transpose is a nu by n. So, this whole thing turns out to have the right dimensions. Okay. And that is the general Fokker-Planck equation. And what we need to do is to apply it to this case out here. And the reason I need this generalization is because this is not linear. In the oscillator case this was linear and I just identified that R matrix and the matter was over, but now this is not linear. So the solutions in general won't be Gaussians or anything like that, they will be fairly complicated things at all. And at the moment we do not know if there is a stationary distribution or not at all. So what does this give us? It says in this case delta rho over delta t equal to, and first we got to do this term here. So exactly as before, you are going to have f in this problem. So let us write down the f xi in this problem is just x and v. F in this problem is equal to there is a v and there is a minus v prime of x over m minus gamma v. Dij mercifully is easy enough, it is exactly as before, because again this is just constants out here, this is 0 out here. What is new in this problem? N is 2, little n is 2 because it is a 2-dimensional object. What is little new? Just 1, just 1. So it is a very trivial problem in this case. So Dij, once again this matrix in this problem is again 0 0 0 gamma k Boltzmann T over M, half G transpose, etc. Okay. So we can write down what this equation is in one dimension. Delta rho over delta t equal to minus v delta over delta x rho. That is one portion that comes from here, because there is a minus, minus. So I took f on the right hand side, so there is a minus sign, okay, and then plus gamma delta over delta v rho, that term will always remain. And then there is a term which is delta over delta v, so this is equal to plus v prime of x over m delta over delta v rho. That is this term plus the usual plus gamma k Boltzmann T over m d2 rho over delta v2. This is the one-dimensional phase space density, conditional density for particles moving on the x-axis alone, just one component, and it has got this extra term here due to the external force, okay, or the potential, applied potential. Everything else is familiar as it stands. This equation is called the Kramer's equation. We will write down generalizations of this to 3-dimensional problems, etc. It is very straightforward to write it down in 3 dimensions. In fact, I urge you to do this as an exercise. Do this in general when you write this as a vector and this equation too as a vector. Now this gamma arises from a fluid and it is related to the viscosity of the fluid, which we will take to be isotropic. So it is the same in all the directions, does not matter, for all the Cartesian components. And this of course will be replaced by the gradient, minus the gradient of the potential. And then for the noise, take this to be eta sub whatever I corresponding to Vi, and eta I is delta correlated such that different Cartesian components are not correlated to each other, okay, and write the general Kramer's equation down in 3 dimensions for the phase space density as a function of vector r, vector v and t. So that is a fairly straightforward generalization. What would happen if you put this particle in a magnetic field? What kind of force does it see? That is an interesting case. I mean, we are going to do this problem, but just to anticipate what is going to happen, what do you think will happen? So I put a magnetic field in some direction like this, and you have this particle moving in 3 dimensions inside a container, a fluid, and it is diffusing, and there is also this magnetic field. What do you think will happen? Well, the particle will tend to do cyclotron motion around the direction of this field, right. On the other hand, it is also diffusing. What is the force applied by this magnetic field on the particle? It is the Lorentz force, right. So there is a Q times V cross B, so there is going to be an extra term on the right hand side which is Q over M V cross B. That force is not derivable from a potential, from a scalar potential which is a function of position. It is a velocity dependent force, but the problem is still very tractable and solvable. Why is that? What is it about this force that makes the problem solvable completely? It is linear in V. So as soon as we have a linear problem, this drift matrix becomes R, which is a constant matrix, and then I have a problem of exponentiating this constant matrix. The green functions can be found, etc., etc. May be complicated in principle, but in practice it is doable completely. So the fact that it is linear is very, very crucial. So this problem can be solved. It is a velocity dependent force. Of course, it is going to look like this term, it is going to have a V, but the difference of course is that V1 dot will involve V2 and V3, whereas this term is just V1 in EB1 dot, etc. So it will mix it up, and secondly this gamma represents the effect of dissipation. As you know, if you put a particle in a magnetic field, a free particle, its energy does not change, kinetic energy does not change. So there is no loss of energy at all. So that portion of the drift term will be reversible in time, but this portion will not be. This is what leads to things tending to an equilibrium, etc. Now tell me, suppose I have a gas of charged particles and there is overall neutrality maintained by some background, and then these particles are diffusing at some finite temperature. Clearly if I put a magnetic field, that field does no work on these particles whatsoever. So will it change the Maxwellian distribution at all? If it is in equilibrium, it should not change this Maxwellian distribution, the temperature will remain exactly the same, nothing is going to happen. But will the diffusion constant get affected? What will happen? What do you think is going to happen to this? Well, we know that otherwise if it is one dimensional motion, we know that this d was equal to k Boltzmann T over m gamma. That by the way remains true no matter how many dimensions the particle moves in, because each Cartesian component the variance goes like 2 dt, and if you have 3 components then the r squared goes like 6 dt. That is all that happens. So the d is exactly the same, kt over m gamma, but now I put a magnetic field, what do you think is going to happen? This isotropy is broken. There is a specific direction singled out by the magnetic field. Will the diffusion along this direction be affected at all? It will not be affected at all because there is no force in this direction at all. On the other hand, in the perpendicular plane, there are 2 other directions in this plane. The diffusion is inhibited because when it tries to diffuse there is this cyclotron motion kicking in. trying to make it curve its path back again. So we are going to discover that this diffusion tensor Dij is not going to be a constant times a unit matrix. It is going to be such that the x and y components are not as large as the zz component. So D33, if you put the magnetic field in the 3 direction, is going to be bigger, and in fact we expect it to be just kT over m gamma, but in the other 2 directions the diffusion constant is going to be inhibited. We will see explicitly how that comes about, but that is just a physical argument. We will write it down explicitly and see what happens here. So this equation here, this basic equation, the Kramer's equation, is a starting point for discovering whether the system has a stationary distribution or not, and so on. What we are going to do now next is to first take care of the problem of the magnetic field, and after that I am going to go back and say let us look at the diffusion process itself, the simple diffusion equation itself a little more carefully, and ask what sort of process is the process x, where the density of x, the probability density of x obeys delta p over delta t equal to d2t over dx2, the original diffusion equation in one dimension, and the corresponding Langevin equation, which in this case was just x dot equal to square root of 2d times a dot t. In the diffusion limit, this means that you have gone to time scales much bigger than gamma inverse, and then the particles is essentially as if the velocity is uncorrelated, it is delta correlated, it is a noise in this case. In this approximation you have x dot is just white noise on the other side, and the corresponding density obeys the ordinary diffusion equation. This is called Brownian motion, mathematical Brownian motion, and this process x, this x process is called a Wiener process, and it is the integral of white noise, because formally what is happening, this will imply that formally x of t minus x of 0 equal to integral 0 square root of 2d times integral 0 to t dt prime a dot t prime. So what we have is a process that is the integral of white noise, and it is much less singular than the white noise itself, which has this delta function kind of correlation, and we are going to ask what is this x of t. It is called a Wiener process, and we are going to study it and its sample parts in some detail. Okay. So that will be the next program, because this thing is what acts as a paradigm, the very model for a random process, as random as you can get in some sense, and it has a lot of interesting properties. Once we do that, I will come back and make a connection between this and the Ornstein-Uhlenbeck process, which, as I told you, is a unique continuous stationary Gaussian Markov process. It is a unique process, and we will see that there is a theorem which will tell you that in some sense, if you have studied this process, the Wiener process, you have studied all Gauss-Markov processes. We will see how this is done by mapping. Okay. So that will be the next target.